Welcome to the lecture. Monday, we start to talk about the multiple unit processes, right? So we have some unit operation, right? Evaporation and boiling and filtration, right? Okay, so I'm sure you all learned this in your high school, but we are, as a college student, we want to know this as a industrial scale. So you need to know what's going on with the industrial scale, right? Okay, and then this is the example of the recycle. Remember, example of recycle. And then bypass is another concept. So bypass is like this is if you go the arrow go to this way, this is recycle. But if you arrow go to this way, this is bypass, right? And we already told you there are some of the cases, example of the bypass. So you learned this already. And then after that, we move to the chemical. The mass balance involves chemical reaction. We start with the stoichiometry, reaction stoichiometry, right? Okay, and then we want to know what is, there are 4 concepts, okay? So please don't talk. If you are chatting, I'm going to ask you to answer the question. Okay, anybody want to answer the question? Anybody want to talk? Somebody's laughing. You want to answer questions? No? No, okay. Then be quiet, okay? Concentrate on what I'm talking. Right, so this is 4.6b. We learned four terms. The first one is limited reactant, right? And then what is limited reactant? What is a limited reactant? If this is a chemical reaction, if I want you to pick up one chemical, and then that is chemical limited reaction. So which one you want to tell me? Is that SO2 or O2 or SO3? Which one? You think of that. Normally you want to think, you want to talk, and if you want to think of what is limited reactant, you will think, well, that's maybe expensive chemicals, okay? And then in the case of this, if you think of SO2 is expensive or O2 is expensive, okay, then I'm sure you don't know the answer, right? How about excess reactant? Excess reactant normally is is cheap. So that's why you want to learn. You want to know that excess reactant. In the case of this reaction, O2 will be the excess reactant, right? Because why? Because you can use air instead of oxygen, okay? And air is free, right? Okay, so that's it. We have some of the example I want to show you here. Where are we? Okay, so let's start from here then. Right, so excess reactant is, have we talked about this before? Yes, we do, right? So if this is the fractional excess. The fractional excess is that if you have, this is excess reactant, oxygen excess reactant, and then if you have 1.5 moles of oxygen involved in this reaction, and then this reaction consumes this reaction, for example, is 2 mole, 1 mole, right? So this is stoichiometric ratio, and then you consume 1.0 oxygen, and then divided by 1.0. So this is the fractional excess. Okay. So what is the fractional conversion? This is chemical fractional conversion is that chemical reaction does not take place instantaneously. and indeed often process rather slowly. So if you think of this chemical reaction, and then it might be slow, and then you don't want to wait. So remember, you will have a separator once the chemical reaction hasn't complete, 100% complete, probably 80% already, and then you have a separator, and you recycle the unused SO2 back to this reactor, for example. So in such a case, it's not practical to design reactors for complete conversion of the limited reactant, right? Okay. So the inference emerged with the sum of the limited reactant still present, and is then usually subject to a separation process to remove the unconverted reactants from the products. The separated reactants is then recycled to the reactor inlet. So this is the one, right? This is what we are talking. And I'm sure you already know this concept because we introduced this to you on Monday. So there's no problem. So today we want to know is that this is the fractional conversion of a reactant. So this is the definition of fractional conversion. So fractional conversion is that the mole reacted divided by mole fed. So for example, this is SO2. You know that how many moles of the reactants fed into this reactor, and then how many moles of this reactant was reacted. So you can have this, you know, according to this formula, according to this equation, you will know the fractional conversion. Okay, for example, 3 moles was reacted, and then you fed 4 moles of the SO2 into this reactor, into this process. So the fractional conversion will be what? Will be 75%, right? Will be 75%. So, and then the percentage conversion will be F times 100%. Okay, so this will be what? This will be 0.75, and this will be 75%. Okay, this is easy. This is easy. So what I want to tell you here is that maybe next week, Kahoot, you need to use these 2 equations to get the answer. So you need to know the definition of the fractional excess and the fractional conversion. Okay? And according to this equation, the fractional excess, normally this is the one, excess reactant. So you only have oxygen to do the calculation. Okay? But for the fractional conversion, it can be SO2 or O2. So it can be limited reactant or it can be excess reactant. So this one, if I ask what's the excess what is the fractional conversion of oxygen? That will be the question, right? Or that will be the fractional conversion of the SO2. Okay? Fractional conversion of SO2. So here I want to give you an example, and then please work with me, and then maybe next week's Kahoot. So this is the example. I'm sure you don't have. I think you don't have the text. Only some of you have the textbook. So anyway, C2H2 plus H2O become C2H6. So you have hydrogen here, and then you get methane. Hexane become hexane, right? So before the reaction, you have 20 kilomoles of the C2H2, and then you have 50 kmoles of the H2, and then you have 50 moles of the 50 moles of the C2H6. So this is the before the reaction. Okay, and then during the reaction, when you do the reaction, you know this is 1 mole, 2 mole, and 0, right? So if I say to you that we found out that hydrogen was consumed 30 kmol. So this will be what? According to this stoichiometry coefficient, this will be 15, right? This will be 15. So this is the text tell you that according to this reaction, there are 30 kilomoles of the hydrogen consumed. So you understand this is, you will consume 15% of the C2H2. And how many C2H6 were generated? 15, right? 15. Okay, this is easy. So as a result, you understand after reaction you have 5 kilomoles of the C2H2 remain, and then you have 20 kilomoles of the hydrogen, and then you will have what? Because it is 50, right? 50 plus 15, that will be 65 kilomoles of the C2H6. Okay, so now I want to ask you the fractional excess of H2. Can you tell me the fractional excess of H2? I give you the formula now here. So the fractional excess, according to this equation, this will be excess reactant. Okay, because if you have 20, that will consume 40, right? So you have this is excess reactant. The excess reactant here is what? H2O feed minus H2 stoichiometry divided by H2 stoichiometry. So the answer will be 50 minus what? 40. You might say, well, Professor, why is not 30? Because it is stoichiometry, because you have 20 here. 20 here, it means that you have to consume 40. So that will be minus 40. So please remember this next week when you do your Kahoot. And then stoichiometry will be 40. So this is the fractional excess of H2. Okay? So this is the answer. That will be 25, 0.25, right? Okay, how about fractional conversion of H2? Fractional conversion of H2 is the definition of fractional conversion is moles reacted divided by mole fed. So the answer is mole reacted will be 30, right? And mole fed will be 50, right? Okay? So you know the answer is 0.6. That's the answer. So next week, Kahoot, I might give you something like this. Okay? And I will ask you excess, fractional excess, or fractional conversion, or fractional conversion of the H2, or fractional conversion of C2H2. Can you tell me the fractional conversion of C2H2? Can you? I'm sure you can. Okay, so please go home and practice this. I'm sure you can get the right answer. Right, so we finished this. We use this equation, use this formula, chemical reaction to show you, to make an example. So why is this? What do we use this SO3? So the formation of SO3 from the SO2 and the O2 is an intermediate step of the manufacture of the sulfur acid. Sulfur acid is H2, is SO4, right? Because if you put this water with this SO3, that will become H2SO4. And also it is responsible for the acid rain phenomenon. Okay? Right. Okay, so I think we finished basic information, basic knowledge of chemical reaction, and now we want to do how to do input equal to output for and there are some general rules. For example, this is the example we just used, right? You have before reaction, during the reaction, and after reaction, so you know what's going on with this chemical reaction. And then we want to do it using symbols. Like this 20, can we use a symbol to represent? For we should use symbols to represent. Okay, this is what we are going to learn now. So this is called general rules for the calculation. Okay. So the first term, you might see that there's a symbol which you might don't know here. This is called Xc. X here. And what is Xc? Xc is the extent of reaction. So extent of reaction, that means if it's 100%, that means chemical reaction completes. Okay, so the maximum is 1. So we use this chemical reaction as an example. Again, C2H2 plus H2, 2 moles H2 becomes C2H6. So before reaction, we use N, okay, NC2H2, NH2, and then NC2H6 as an example. And then during the reaction, you know, Xc is the extent of reaction. So you can have minus 0.5 Xc, minus 1 Xc, and 0.5 Xc. So what is this? This is extent of reaction. As I just told you that the maximum here is 1. So it can be 0.6 or 0.9. This is how reaction can be completed. And then as a result, after reaction we use this is the one. This one minus this one, right? This one minus this one. This one minus plus this one. Because this is reaction, this is minus, and then the reactant is minus, the product is plus. I'm sure you already know this. No problem. So the things you need to learn is this is called Xc. Xc is extent of reaction. And if you use Xc over dot, that means what? This is more flow rate. Okay. And then remember, this is called stoichiometry coefficient. So stoichiometry coefficient, we use nu as a symbol to represent stoichiometric coefficient. Again, let's use this as an example. So C2H2, that will be minus 1, right? Because it's reactant, and then the sign is negative. And then H2, again, is a reactant, so the sign is negative. So this stoichiometric coefficient, this is 1, this is 2, right? And then this is plus 1, C2H6, that's plus 1. This product. The product will be, the sign will be positive. Okay? And then input and output. This is, remember, this is what we call input. N sub IO is that the moles of the species I in the feed. Ni, there's no zero here, is the mole of the species I in the outlet. So you have input and output. So as a result, you can use something like this. You can use Ni, this final product. The after reaction, this is the reactants after reaction. This Ni equal to this one, Ni0 plus nu times Xc. So nu times X is, this is what? This nu is what? Stoichiometric coefficient. It can be 1, minus 1, minus 2, or it can be 1. Okay, X is external reaction. It can be 60% or 0.6, 0.3, 0.5, for example. So if you use this as an example, so you can see, for the example of the C2H2, this is the one after reaction. So you use Ni, N sub I to represent this one. So Ni can be Ni0, Ni0, this is the Ni0. This plus nu times Xc, this is minus 0.5. As you can see, 0.5 minus 0.5 is what? This is this one, right? This 0.5, and then Xc will be here. So as you can see, this is the one you use like this. So let me summarize this. The general rules for the calculation is that before reaction, you have, in the beginning, you have chemical, you have some moles of the reactants and products. And then during the reaction, you consume some of the reactants and you generate some products and use this nu times Xc as a symbol. And after reaction, you have this plus this, and you use NC2H2 equal to this one. this plus this. As you can see, the nu here is a negative sign. Nu here is a negative sign, and nu here is a positive sign. Okay? So you put a symbol here, and then you use plus. Okay, the reason we want to use symbol is that this is the general rules or general cases. So you can apply it, you can use computer to do the calculation easily using these symbols. So it doesn't matter you have 10 examples or 100 examples. If you use this, you just input the numbers, and that the symbols will do the calculation, will represent the numbers and do the calculation. Computer will do the calculation for you. Okay? Right. So important thing is the final mass will equal to what? Initial mass plus reaction. Mass reaction or are generated or consumed. Okay? Or moles, final moles will equal to initial moles plus the moles generated or moles consumed. And you might say, well, Professor, general balance equation tells us there are 5 terms. Where is accumulation? Well, in this case, in all the cases, we always talk about steady state. Basically, we talk about steady state. We don't have any accumulation, terms of accumulation. Okay? So again, output, you can say output equal to input plus generation or consumption. Okay? Because you consume here, you generate something here, right? Or this is the flow. This is the if we have overdot, that means flow rate. That represents the same thing. Okay, so this is another example, which is Haber reaction, right? Reaction for ammonium created by Haber. Okay, the fraction, and this example tells us that the fractional conversion of X is 0.6 hydrogen. So as you can, let me start to do this. So before reaction, for example, we have 100 moles per second. That means the continuous process, right? Okay, and then in the very beginning we have 300 mole per second, and then we have 0, and we have this is argon air. Argon, it should be argon, right? Argon. Right, and we know that the hydrogen conversion is 0.6. So you know the Xe will be 0.6. So in the case of here, that will be 300 moles times 0.6. That means you consume 180 hydrogen. So according to the stoichiometric coefficient, is if you consume 3 moles of the hydrogen, you need to consume 1 mole of nitrogen. So in this case, if you consume 180 moles of the hydrogen, that means you will consume 60, right? 60 moles of the nitrogen. Okay, remember this is a negative sign here. And then how many ammonia you generated? 120, right? 120. Okay, this is very easy, so I don't want to waste your time. So as you know that this will be 100 consume 60, that will be 40, and this is 120, and this is 120. Okay. So I might want to ask you what's the fractional what is the fractional conversion of the hydrogen in this case? And you need to remember the equation and then tell me the answer, right? Okay. Hope you remember equation. Right. So Next will be the example. I want you to work with me, 4.6-1, 4.6-1. That will be in your textbook, page 112, example 4.6-1. On Monday, there's one of you come to me say that he cannot find PDF file. And I talked to teaching assistant, and I'm sure you received an email, right? So I think this you can have PDF file today or coming. I want you to work with. I want you to get the PDF file, and then we can work together with this example 4.6-1. Right. Okay. So. But before we really talk about this example, this is acrylon nitrile. Let's start to understand what is acrylon nitrile. Acrylon nitrile is an important monomer, okay, of the manufacturing some useful plastics, and its colorless liquid often appear yellow due to the impurity. Okay, so again, in order to do the production of this one, you need to have this C3H6 and ammonium. So ammonium can be from nitrogen and hydrogen, right? And where can you get this from? From crude oil. Remember, we have fractional distillation. The fractional distillation column will produce this one. So you can have this, and with oxygen, then you can produce alkaline nitrile. Okay, this chemical. Of course, we want to do it in an industrial scale. So it looks like this. A lot of towers, right? Okay, and once we get this chemical, what can we do for this chemical? As you know, that this is called monomer. Acrylon nitrile is a monomer. So we use monomer to make some polymers. Monomer become polymer. Okay, so acrylon nitrile is a key production materials for many products. Okay, so you can make some fibers, you can make some rubbers, and use these fibers and rubbers to make the products like gloves, suitcase, something like this. So this is an important and useful chemical. Right. So you can learn this when you are third year, fourth year, or in a postgraduate student. As a postgraduate student, you can learn this, how to make this. But as a first year, we just want to know how to do input equal to output. So let's go to the page 112, example 4.6-1. Read the text, right? Let's read the text. A single chemical reaction A become 2B. Okay, is this one? That's right. Sorry, I'm sorry, this is another one. Acrylon nitrile is an intermediate used in the production of a number of polymers, right, including nylon, blah 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 blah. Okay, and then let's go to the end of this paragraph. The primary means of the synthesizing acrylon nitrile is among us oxidation of the propane. So the formula here, C3H6 plus ammonium plus oxygen become acrylon nitrile, right? Plus what? H2O. Okay, so and the second paragraph, the feed to a propane like C3H6 ammonia oxidation process contain 10% of the propane, C3H6, right? 12% ammonium and 78% air. Okay, so let's say that we have chemical. Let's take a look of the slide here. The chemical reaction, before the chemical reaction, you have nitrogen, and then you said 10%, right? Let's write down 10. For example, 10 mole. Okay, it can be 10 mole, right? Okay, 10% and then 12% ammonia, and then 78% air. 78% air means what? Because 78% air means you have to times 21%, which is 16.4 oxygen, right? Because air contains 21% oxygen. So in the slide here, you will see that it's something like this. So actually, it's 10 moles of the C3H6, 12 moles of NH3, and then 16.4 moles of O2. Okay, this is the information you got. And then in the second paragraph, the line 2, a fractional conversion of 30% of the limiting reactant is achieved. So you know this is kind of specification, which tell you that you need to find out which one is limited reactant among which one among the C3H6, NH3 or O2. Which one will be the limited reactant? And this limited reactant, the fractional conversion is 30%. Okay. And then let's go to next. Taking 100 moles of the feed as a basis. So as I just show you 10 mole, that means 10%, 10 more percent will become 10 more, right? 12% more ammonia will become 12 more. Right, so let's determine which reactants is limiting and the percentage by which each of the other reactants is in excess, and the molar amount of the all products gas constituent for 30% conversion of limited reactant. Right, so this question or this example wants us to find out which one is the limited reactant. So if you take a look of the slide here, I'm sure this is easy because this is 1 mole. If you consume 1 mole, this will consume 1 mole. This will consume what? 1.5 mole. So if you consume 10 mole here, you consume 10 mole here. So you have 2 more left. And you will consume what? You consume 15 moles here. So you have 15 moles here. Okay, so the thing is, which one is limited reactant? Or which one is the most things left? So let's see, let's take a look of this. In the beginning, this is 0 and 0, right? It's 0 and 0. So that will be 10, 12, 16.4. So the basis is 100 more feet, right? 100 more feet. And then find out limited reactant. So as you can see, this is, if this is C3H6, C3H6 and NH3, that will be, this one will be equal, if we got stoichiometry coefficient, 1 to 1, the ratio will be 1, right? But actually this is more than 1, so you understand this one and this one is limited reactant. Okay? So NH3 is excess. This is limited reactant, this is excess. Okay, and then if it's NO2 and then NC3H6 compared to this one and this one, this is 16.4 divided by 10. That means this is greater than 1.6, right? So O2 is excess. So as you know, this is compare this and this is excess reactant. This and this is excess reactant. So this one must be the limited reactant, right? Okay. So before I show you the mole here, and you understand oxygen is always cheap, right? You don't know which one is more expensive, but you understand this is cheap. So this one will be excess reactant. But which one, compared to this one, which one will be limited reactant? If you don't know, you just do use the this stoichiometric coefficient or stoichiometric ratio to compare which one is excess reactant, which one is limited reactant. So you know that this is more expensive, this is a limited reactant. So C3H6 is limiting reactant, and this one only consume what? This the conversional the fractional conversion is 30%. So fractional conversion is 30%. That means what? The fractional excess of the NH3 will be what? If you think of this, that will be 12 minus 10, right? 12 minus 10, because you consume 10. The fractional excess will be divided by 10, that will be 20% excess. Okay, the fractional excess of oxygen will be what? Could you please tell me? It's easy, right? Easy. So that's 16.4 minus 10 times 1.5 and divided by 10 times 1.5. That will be 9.3%. Okay? Right. So the specification of the C3H6 fractional conversion is 30%. 30%, right? So this is limited reactant, and then only 30% consumed. So as you know, during the reaction, you have 10 times 0.3, that will be minus 3 here. And minus 3 here, you will be minus 3 here. And then that will be 4.5, right? And here will be plus 3, and then plus 9. So after reaction, 10 minus 3, that will be 7. 12 minus 3 will be 9. And then, as you can see, you got the old answer here. So it doesn't matter what the question asks you, as long as you find out this one, you can get what the example want to know. Okay? So another important information is that when you see their input, there are 4 species: C3H6, NH3, and O2, and nitrogen. That's input the 4 species, but output will be 6 species, right? 1, 2, 3, 4, 5, 6, because you have 2 products come out. So when you do the input equal to output, you can realize that that's the way you want to know. The important thing is Ni equal to Ni0 plus nu times X. Okay? Right, so I finished this 4.6, and then now let's go to the 4.6C, chemical equilibrium. In the chemical reaction engineering, you know that the chemical equilibrium thermodynamics is always talking about the very beginning and in the end. So it's nothing to do with the what's going on during the process. But for chemical kinetics, is how long will the system take to reach a specific state short of the equilibrium? That means what? That means the thermodynamics, chemical thermodynamics is always talking about in the initial state and final state. You don't need to worry about what's going on during this process. Okay? So nothing to do with time. You just know first initial stage and final stage. But for chemical kinetics, you need to know what's going on during the process. Okay? So when you have, it's always something to do with time. That means I might want to know that what's going on in the 10 minutes, after 10 minutes reaction, what's going on with these chemical reactions. Okay? So this is one of the topics is called chemical equilibrium and thermodynamics, and also chemical kinetics. And the other thing is that irreversible and reversible reaction. So this is time, reaction time, right? This is reaction rate. So in reversible is single direction. Just now we always talk about irreversible chemical reactions. For example, this is only one direction. So the balance is that the concentration of limited reactants eventually approach to zero. So the reaction rate will be very high in the very beginning, and then it will reaction rate will go to zero in the very end. Why? Because it's always go to this direction, and eventually you will only have this chemical without some of this, right? So reaction rate will be decreased all the time and then reach to zero eventually. And how about reversible? This is the example of a reversible reaction. C2H4 plus H2O, it can become C2H5OH. What is this? Ethanol, right? Alcohol. It can go this way. This is A direction. It can go. So the reaction rate will be very fast in the very beginning, and then it will become a steady state. It will become a constant rate in the end. You might say, well, Professor, why not? It's not going to hit this direction? Because it is reversible. So in the beginning, the reaction rate will become very fast, and it reach to a certain constant, reach to a constant level. And then reversible, this direction from the right to the left, it will go up to this way. So eventually, the rate to the right hand from left to right will become equal to the rate from left to the right. So this is irreversible. This is reversible. Okay. So balance is the rate of the forward reaction, and the reverse reactions eventually are equal. Right. So I think let me think. Should I? Okay. So this is the example of 4.6-2 calculation of equilibrium composition. We need to do the example like this. So let's go to the page 114. 114 here is the calculation of equilibrium composition. So this is the chemical. This is the chemical reaction. Carbon monoxide CO plus H2O equal to CO2 plus H2 hydrogen. Right? Okay. Let's start to work on this. The numerous chemical processes has been designed to produce hydrocarbon products from fossil fuel. Is this one? Okay, good. The first coal, oil, or natural gas. The first step in such processes often involves conversion of the fossil fuel to a mixture containing carbon monoxide and hydrogen, followed by water-gas shift reaction, which adjusts the ratio of these species to a desired volume. Anyway, so the chemical reaction, you can see a CO plus H2O becomes CO2 and H2. So this is a reversible reaction, right? So assume the reaction proceeds to equilibrium at a temperature T. So you know the temperature T, and the mole fraction of these four reactive species satisfy the relationship. So you know this, you learn this in the high school. So this is what we call what? Equilibrium constant, right? So Y is kind of what? Y is a fraction of the CO2, right? Y CO2 is the fraction of CO2. YH2 is the fraction of the H2. Okay? Divided by, this is output. This is the product. The reactant will be underneath of this product, right? Divided by YCO and times YH2O equal to K. K is equilibrium constant. So temperature is 1105, right? Kelvin. The K is 1. So you know the K is equilibrium constant 1. So the third paragraph, suppose the feed of the reactor contain 1 mole of CO, 2 moles of the H2O, and no carbon dioxide and no hydrogen. And the reaction mixture comes to the equilibrium at 1105 Kelvin. Calculate equilibrium composition and the fractional conversion of the limited reactant. So you need to calculate the equilibrium composition and the fractional conversion of limited reactant. That means what? That means you need to understand what is the fraction of the CO and fraction of hydrogen and fraction of carbon monoxide and fraction of H2O, right? Okay. So let's go back to the slide here. So the slide here is all the information we know is before reaction, that will be 1 mole, right? 2 moles and 0 and 0, right? And during the reaction, the reaction is that what? You don't know, because you don't know X eternal reaction. You don't know this. But what you know is stoichiometric coefficient is -1, and this is -1. And this is 1, and this is 1. X E stand for equilibrium. Okay? E stand for equilibrium. So after reaction, you will have 1 minus Xc sub E, and you will have 2 Xc sub E, and this will be E, FCE, FCE. So this is after reaction, and then you understand equilibrium coefficient is K equal to 1. So according to equation, according to this, you know that this is total 3 moles. And you need to find out the fraction, right? K equal to 1 and equal to this, right? And then equal to what? Equal to this. You know, you want to find out the fraction, that will be what? That will be CO2 is here, right? CO2 is here. So Xc divided by 3 times Xc divided by 3 divided by the fraction of the CO, fraction of O2, H2O. And this is equal to 1. So the thing is that you can find out this is quadratic equation, 一元二次方程式, right? So you can find out Xc. Xc is 66.7%. So this is eternal reaction, right? Okay, so you understand this. So if you put the numbers here, you got the answer. So fractional conversion of limited reactant. What is the fractional conversion? Limited reactant is what? Which one is limited reactant? If you had told you this and this, it's easy for you to find out. Water is very cheap. Carbon monoxide is expensive. So carbon monoxide will be limited reactant. Of course, you have 1 mole and 2 mole here. So if you don't have common sense of this, so you might know that this carbon monoxide is limited reactant. So fractional conversion, please write down for me. This is the answer. Okay? Right. Okay, so next topic will be multiple reactions, because we already know the reversible reaction, irreversible reaction, and now we want to know what's the multiple reaction, what's going on with multiple reaction, input equal to output, and then yield and selectivity. But before we talk about this topic, let's play Kahoot. So the section 4.6D is we want to know 2 terms, the yield and selectivity. Again, I want you to know this because this might show up in the question of Kahoot next week. So the multiple reaction normally involve desired reaction and the side reactions. You can have side reaction or you can have side reactions. So it can be multiple. Okay? So side reaction can be 1, 2, 3, 4. So here I give you an example of the C2H6 reactions. You know, C2H6 reactions is that this is what we call dehydrogenation. So you take out one pair of the hydrogen atom, become hydrogen molecule. So this is called dehydrogenation. You take out one pairs of the hydrogen atom. Okay, this is what we want. But however, this reaction can have some kind of reactions because hydrogen will react with H2, C2H6 again. It becomes methane. This is a side reaction. And methane, because this is inside, and C2H4 can also have chemical reaction with C2H6 and become C3H6. This is another side reaction. And these two are not the one you want. Okay, this is called, this is desired reaction. These are side reactions. So if you write down, if you want to do input equal to output, and then you will know that you only have one reactant, C2H6, into this reactor. But how many outputs you will have? How many outputs? You can have, if you don't have completed reaction, you have C2H6, right? Okay, you might react completely, but you might have some left. It depends on internal reaction, right? Okay, and you will have this one, C2H4. And you might have CH4. You might have C3H6. You will have H2. So you have one input, and you will have 5 outputs. So what happens if you just want C2H4? You might have another kind of process to do the separation, right? To do the separation. So one species input, and there are 1, 2, 3, 4, 5, right? 4 to 5 output species. So one input and 4 to 5 outputs. So the thing is, we want to know how good is this reactor, right? How good is this reactor? Of course, we want to get as much as we can of the C2H4, and we don't want this. So this is a term we call yield. So the definition of yield is that the moles of the desired products form. So this is how many moles of C2H4 in these three reactions, and divided by the moles would have been formed if there were no side reactions. So if there's no side reactions, if you have one more input, you have one more output, right? So this is, and then if there is no side reactions, and limited reactant has react completely. Remember, limited reaction, this one, limited reactant will has react completely. So according to this definition, you can calculate the yield. Yield is 良率, right? 良率 or 产率. Okay. Okay. For example, if you produce 40 moles of the C2H4, and if there's no side reaction, you can produce 50 moles of C2H4, C2H2. That's C2H4. Okay, so that means what? That means the yield will be what? 80%, right? I'm sorry, you change this to C2H4. Okay, right. And the second term is called selectivity. Selectivity means if you have 4 products, 1, 2, 3, 4, right? You have 4 products, and then what's the selectivity will be? If the selectivity is higher, then you get better. Your reactor is better, right? So the definition of selectivity is moles of the desired product form, which is C2H4 in this case, divided by moles of undesired product form. Okay, it depends on definition. For example, H2CH4 and then C3H6. This is called selectivity. Selectivity. Or we can, the different definition, we can have the selectivity of C2H4 and the H2. I can ask you something like this. It can be 3 of this, it can be 2 of this, it can be 1 of this. Okay, it depends on what the question asks you. For example, the selectivity of the C2H4 to H2, or the selectivity of C2H4 to others from a side reaction. Okay, side reaction is these two, right? Or selectivity of C2H2 to the rest of the products and reactants. Not reactant, products. Sorry. Okay? Right. So let's say that the reactor here, you have one input. Limited reactant react completely, and you have, if this limited reactant react completely, you will have 4 output, right? 4 output. So the EA will be, as I just showed you. Please remember, there's no side reaction, right? The selectivity will be C2H4 and divided by moles of the CH4, H2, and the C3H6. Right. Okay, so how can we do the balance in multiple reaction? Again, this is Ni equal to Ni0 plus nu times Xe, right? That's what we learned just before the Kahoot. And then how about multiple reaction? Multiple reaction is easy because what? Because this is output, this is input, so there's no change. So this is output, this is input, plus what? Because you have, for example, you have 3 chemical reactions, so you have 3 nu times Xe. So you just do the summation of nu times Xe. Okay, one chemical reaction, this is only nu times Xe. But if you have 3 chemical reactions, you have 3 nu times Xe. You do the summation. Okay, so this is the things you need to know. So here is the example. There are 2 chemical reactions, and then reaction 1, you have Xe1, right? Internal reaction is always the same for all the components in the single reaction, right? So this Xe1, Xe1, Xe1. So this is minus minus plus, right? For the nu here. Okay, and how about this side reaction? Side reaction is this one, and you have Xe2, Xe2, 3Xe2, and then 2Xe2 and 2Xe2. So as a result, input is this one, right? Input is this one, and then reaction. Remember, this is input. We don't know that this species, this species, this species, this species, and this species. So reaction will be 1 plus 2. So this is Xe1 times plus Xe2, right? This is half Xe1 plus 3Xe2. This is Xe1. This is 2Xe2. This is 2Xe2. Okay. So output will be what? Output will be this plus this, right? And of course you need to do the minus. You need to do the minus because the nu here is the minus. This is the example of this C2H4. Okay, and you can do this. You can do this, this, and this. Okay? Right, okay. Do we have time? Yes, let's finish this example. Okay, this example is the 4.6-3 yield and selectivity in a dehydrogenation reactor. Dehydrogenation we just learned. right? So you take out one moles, take out one pairs of the hydrogen atom. So let's start page 117, example 4.6-3. So in the slide you can see there are two reactions, right? The first one is the main reaction. The second one is side reaction. Okay, the reactions take place in a continuous reactor. So continuous reactor is a steady state. So accumulation will be equal to 0, right? The feed contains 85% moles SM, C2H6, and the balance inert. So you have inert here. Okay, so you have 15% more of inert. Okay, the fractional conversion of ethane is 0.501. Okay, the fractional yield and the ethylene is 0.471. So they give you two informations. The first one is fractional conversion, ethylene is 0.5, and the fractional yield of ethylene is 0.471. Calculate the molar composition and of the product gas and the selectivity of the ethylene to methane. So you just want to know selectivity of ethylene and methane only. So this is the question you want to answer. But it doesn't matter how complicated of this question. The principle is that you need to know that if you go to the slide here, you need to know the Xe1 and Xe2. You need to find out these two. And you got all the answers. Okay? So let's draw the flow chart. This is reactor. There are 85% moles of C2H6. And then of course you have 15% moles of inert gas. The basis you can use as a 100 mole, right? So 100 mole here. And then what you don't know is C2H6 come out, and then C2H4, because C2H4 here, and because this is not 100% completely reacted. So you have C2H6, you have C2H4, you have CH4 here, and you have H2 here. So that's what you don't know, but you know there are two specifications, right? So according, this is hydrogen here. So according to the, N5, actually N5 is equal to this one, so don't worry about this. So the solution is that you need to, if you use ethanol reaction to do this, the final product equal to input plus summation nu times Xe. So that's what you need to know. So reaction 1 is Xe1, right? So you have reaction 2 is Xe2. Okay? So again, you start to do output equal to input plus nu times Xe. So let's find out what you can get from this equation. So for C2H6 is here. So it's N1, this is N1, right? So N1 is output equal to what? 100% input. Input is 100 times 0.85, right? Minus what? Xc1 and Xc2. So this is input plus summation nu times Xc. Nu is minus 1, right? Minus 1. So it's minus here. How about C2H4? C2H4 is N2 here, right? Output equal to input. There's no input, right? 0 plus Xe1. Because this is only 1 here. There's no Xe2. And you know this is 1 more. And methane CH4 output here, output equal to 0. There's no input. Plus output, the first one, there's no Xe1 because there's no C2H4 in the first reaction. The second reaction is what? You have 2 moles generated. This is nu is 2. So you have 2 times Xe2. Okay? And H2 and hydrogen is here. N4 and 0, Xe1 minus Xe2. So this plus Xe1 minus X2. Okay? And the inner gas, you know that. So the things I mark in yellow color, red color is unknown. So according to this, can you get XC1 and XC2? Can you get N1 to N5? Of course you can get N5, but can you get N1 and to N4? No, you cannot. Because there are two specifications. One is the fractional conversion of ethylene. So which is 0.501. 0.501 is mole reacted minus mole fed. So mole reacted, where is the mole reacted of the C2H6? This one, right? Okay? And the mole fed will be 85. Right? So you have a absolute sign here. So you get an equation, you get question 1. Question 1. And question 2 is the fractional yield of ethylene C2H4, which is 0.471. So according to this definition, you can find out this is moles would be formed, no side reaction. If you have 85 here, you can form 85 here. If you have 85 here, you can form 85 more here. And this moles of the desired product, what's that? The XC1. XC1 here. Okay, so according to this one, you can get XC1 40. And you go back to the 0.4, which we get the XC2, 2.6. Right, okay. So once you got XC1 and XC2, so there's no problem. You got XC1 and XC2, no problem to get N1 to N4. Okay, so what's the selectivity of the C2H4 to C2H4, CH4, which is N2 divided by N1, and you know this one, and you got the answer. Okay, right. So so I think that's it for today. Important thing is the selectivity and yield. There are 4 things you need to remember, and that will be show up in the Kahoot next week. Fractional excess, fractional conversion, yield, and selectivity. You need to know the definition well. Okay? Right, so that's it for today. Before you go home,